please give a warm round of applause to welcome Josh Lothringer.
Thank you for the introduction. I'm Josh Lothringer. Today I'm going to talk about exoplanet atmospheres. A little bit about where I came from. So I did my undergrad at the University of Colorado in Boulder, Colorado. And as mentioned, I worked on the Kepler Space Telescope. So I had the extraordinary opportunity to work at mission operations at the Laboratory for Atmospheric and Space Physics. And there I worked on a couple other satellites. A lot of them were Earth-based, looking at the sun and stuff. But one of them was the Kepler Space Telescope. And I was actually able to be one of the people that actually sent the commands to the spacecraft. And so that's what got me interested in exoplanets. But what got me interested in atmospheres was some of my work with the MAVEN mission to Mars. So that's a mission that's orbiting the planet Mars, looking at the upper atmosphere to see how its atmosphere escapes. So that's what got me interested in atmospheres. So when I combine the two, that's why I'm looking at exoplanet atmospheres. So here in Arizona, I've worked on a couple projects. One of them was using the MMT telescope, which stands for the Multi-Mirror Telescope, which is a telescope at Mount Hopkins. It's maybe 40 miles down the road. And it used to have a bunch of mirrors. So that's why it was called the Multi-Mirror Telescope. But it actually got replaced by a big mirror. So it doesn't actually have any multiple mirrors, but they still call it the MMT for some reason. But it's on this big, giant telescope that actually is a building that can rotate, look at any place in the sky you want. So I looked at exoplanets with that telescope, but I've also had the opportunity to use data from the Hubble Space Telescope and the Space Telescope Imaging Spectrograph. So that's this box right here. This is a picture of it getting installed on the Hubble Space Telescope, which is this guy here by an astronaut on the space shuttle. So that's just a little bit about what I do. But what I'm talking about is exoplanet atmospheres, and why are exoplanet atmospheres interesting? And so it's what I chose to do my PhD on, so I obviously think it's super interesting, and here's why. So when we look at an exoplanet and we just detect it, we can only measure a couple properties. So we can only see how much it weighs, basically its mass, and how big it is, what's its size. But besides that, the atmosphere is all we get. So that's basically the only information that we can piece together what its origin and evolution and current nature is. So the atmosphere is luckily able to tell us what the planet's made of, how hot it is, or maybe what the weather's like. And we can compare it to our own solar system, which is important. We can actually go to planets like Venus and see and compare their atmospheres with the atmospheres we see on other exoplanets. And as mentioned previously, biosignatures are a really important aspect of all this, because we might actually be able to detect life through looking at the atmosphere. Okay, so a little bit about what I'll talk about. I'll talk about the techniques that we use to analyze the atmospheres. I'll talk about some of the things we found out, and I'll also mention future instruments, telescopes, and missions. Okay, so two techniques we use are transits and direct imaging. Here's a GIF, actually, of Venus transiting the sun. You can actually see Venus here. This is a transit from a couple of years ago where we actually see Venus crossing the disk of the sun. But we can do this with other planets around other stars. We're not actually able to see the disk of the planet of other stars because they're too far away. They're just pinpricks of light. But what we can see is that the star gets a little bit dimmer when the planet passes in front of it. And so that's how we can tell how big the planet is the deeper or the more, the dimmer the star gets, that means that the planet is bigger. There's another method called direct imaging where we actually take a picture of it. So transits are a unique but indirect way to look at a planet. But with direct imaging, we can actually take pictures of them. So this is a GIF of the planet system called HR 8799. And there we were actually able to image 4 separate planets. So there's one right there, there's another there, and one out there. And so over the course of 6 years, we're actually able to take pictures of them throughout their orbit, and we can watch them move. I think this is just amazing. These are very far away from their star. They have to be. The inner star is very bright, so it's hard to find planets that are close to the star. So they have to be young, very big planets that are very bright, away from their host star. So this is kind of limited. We can't look at Earths around other stars. So some of the good things about transits are it's good for close-in planets. We can study things right next to their star, because we're not actually trying to separate the starlight. We're actually looking at an indirect method to try and detect them and look at their atmospheres. Importantly, right now it's the only way we can look at habitable atmospheres. We don't have the technology to directly image planets really close to their star. So this is the only way we can get information about habitable exoplanets. But direct imaging is probably the future, and where eventually we'll get to imaging Earth-like planets. But right now we can only image far out young planets. Because you need really advanced technology to actually be able to separate the light from the planet from the star. You need really high angular resolution is what we call it. But luckily the University of Arizona is really good at doing this. We've built many instruments that are actually capable of finding some of these planets. Okay, so I'll talk a little bit more about transits and eclipse and what we've actually learned from them. So here's a GIF of a planet, a hypothetical planet passing in front of a star. And as it's on top of the planet, it blocks some of the light, so we see the brightness go down a little bit. And based on how big the planet is, the depth will be a little bit bigger. So here's some actual data of a planet called 55 Cancri E. It's a planet that's maybe twice as big as the Earth around a star that's a lot like the Sun, but it orbits 10 times closer than the planet Mercury. So it has a temperature of something like 3,000 degrees Fahrenheit, which is actually enough to melt iron. And so it's enough to melt the surface of this planet. So it's probably a lava world with maybe seas of lava. But we can actually look at this planet using this transit technique. So we can actually see the planet as it passes in front of its host star. We can see it emit some of its own light. We're actually able to see that it gets a little bit brighter as we look at its day side. That's the hottest part, so it'll be emitting a whole bunch of light. We can actually see that little bump. And then we can see it pass behind its star, where we're no longer seeing the planet, so all we get is the starlight. So you get a little bit of a dip when you eclipse it. So we can see all these features in this planet just from the fact that it transits. And this thing's a pretty small planet, actually. It's only twice the size of the Earth. A lot of the planets we look at are called hot Jupiters, which are big Jovian, Jupiter-like planets that are maybe 10 times the radius of the Earth. And so with transits, we're actually able to do spectroscopy. This is something that was mentioned before. So it's as when you pass light through a prism, you get some lights. This is, of course, Pink Floyd, but this is a very useful diagram, actually. So we can do this with light from stars and stuff. So this is the colors that your eye would see, everything from blue to red. There's also infrared light, which is redder than the red that our eyes can see, and ultraviolet light, which is bluer than our eyes can see. But what's important is that different gases give off different colors. These are called spectral lines. And so we can see hydrogen gives off a few unique colors, while neon gives a little bit more, and iron actually gives off a lot of different colors. You can see he's got these really blue lines. And so this is how we're actually able to identify gases in an atmosphere. When we can detect these lines in an atmosphere, we can say, oh, this planet has hydrogen or has neon or iron. We've actually been able to do this for a handful of planets. Some of them are the hot Jupiters I mentioned just before. So these are big Jovian planets, 10 times closer than Mercury is to our sun. So these can be thousands of degrees, but they're really easy to observe. So we actually know a lot about them. So two elements that we've actually been able to detect in their atmosphere is sodium and potassium.
these have big spectral lines. So the sodium one is like a yellowish. It's actually what some streetlights are made of. So whenever I travel down Mountain Avenue has a bunch of these. So I always think of Exoplanet Atmospheres when I go down Mountain Avenue. So we've been able to detect sodium and potassium. We've been able to detect water vapor in some of these really hot planets. Some of these hot planets also have clouds of rock. So things that would be rock on Earth are actually it's so hot on these planets that you can get clouds of these in liquid form. We've discovered that some hot Jupiters have really strong jet streams. So these are really strong winds that are hundreds of kilometers per hour that are going all the way around the planet, trying to transport this hot air, because it's so close to its star, trying to transport hot air to the cool night side. We've also been able to detect clouds. So clouds are actually evidenced by having this spectrum be really flat. So a lot of our spectra for small planets are pretty flat because they just look gray because they're covered in clouds. And these clouds they're not water vapor because it's too hot for that. So what they're actually clouds of are salt, so it's things like potassium chloride. We've actually been able to find some exoplanets that have escaping atmospheres. Here's an example of a planet, GJ436b, and then its host star, GJ436. They're actually so close to each other that the planet is losing its atmosphere. So we've detected this big cloud of escaping hydrogen. So it almost looks like a comet. So I'll talk a little bit about directly imaged exoplanets and what we know about their atmospheres. So there's only a handful of directly imaged exoplanets that we've been able to detect. Like I said, it's really hard. We've only been able to detect really big planets far away from their star. And it turns out there's not a lot of them. So this is actually most of them. There might be a few more that we've detected. But there's definitely more hot Jupiters and planets closer in than there are farther out. This is the one that I showed earlier, HR 8799. There's some other systems that we know about. So this is the GIF that I showed before of HR 8799 as they orbit their planet. But here's another cool one of Beta Pictoris b. So this is a planet that instead of looking face on, we're looking edge on. So this planet, as it orbits, will appear as if it's getting closer to its host star. So this is over the course of about a year or two. We could watch its orbit change. So what do we know about directly imaged exoplanets? There's not a lot of them. We only know a little bit at this point, but we've been able to detect things like water vapor, carbon monoxide, and methane in these planets. Some of them also have clouds like the other planets. Like I said, there's not many of these stars, so what we think is there's not a good way to form these planets so far away from their star. So what we need to do is improve our technology so that we can look at planets closer in. And there's a lot of people trying to do that, especially here in Arizona. So one concept to do this is called the star shade. This is really cool. This is all in space. You have a telescope on one end, and then really far away, you have this little pedal thing that blocks out the starlight. So you're actually able to see planets orbit a bright star because you're able to block out all that starlight. So this is maybe something that would happen in the next decade or two. So I'll list a couple of not a couple, there's a good list of future missions that I'm getting really excited about. So there's ground-based surveys looking for more exoplanets. You may have heard of the TRAPPIST system, which is a system of 7 Earth-sized planets around a small star. That was just the first planet found by this telescope, by this big survey. So there'll be more like it. TESS is this a mission like Kepler. So Kepler was looking for exoplanets. It was looking for it to planets to transit their star. But what TESS is going to do is it's going to do that, but across the whole sky. Kepler only looked at a small patch of the sky, but TESS is going to be able to look at the whole sky and survey a whole bunch of exoplanets. So we'll probably find thousands of more exoplanets. And what's really exciting is this actually launches next month on a SpaceX Falcon 9.
There's another mission that'll probably launch this year as well, called KAOPS. It's led by the Swiss and the European Space Agency, and it's another space telescope that'll measure radii of these planets really well. JWST is really exciting. I'm actually preparing a proposal this week to try and to try and get some time to observe with James Webb. This will probably launch next year, but it's got a suite of instruments that'll just blow all the data we get with Hubble out of the water. We'll learn so much with James Webb because we'll be able to look really far into the infrared. So we're going to find molecules that we hadn't been able to find before, like methane and CO2 in things like hot Jupiters. It's also going to be able to directly image some stuff. It's got a coronagraph, which is one of those things that blocks out the starlight. It's got one of those as an instrument, so it's going to be able to look at things like protoplanetary disks and directly image some new exoplanets. There's WFIRST. So this is actually a mission that was designed to look at dark energy and dark matter, but it turns out it's going to be really good for exoplanets too, because it also has one of those coronagraphs that blocks out the starlight. So we'll be able to directly image stuff, but in the optical. So we'll be able to see reflected light off of these planets. This will give us a really good idea of the types of clouds, the particle sizes of the clouds in some of these hot Jupiters. People are already beginning to plan for what happens after James Webb Space Telescope. So there's a couple mission designs. There's HabEx, LUVOIR, and OST. So HabEx is another directly imaged exoplanet mission to try and directly image them. LUVOIR is going to be like a really big James Webb Space Telescope. So that's what I showed here. I like it because it stands for the Large Ultraviolet Optical Infrared Telescope, but they just pronounced the acronym as French, so it's LUVOIR. Then OST is the Origin Space Telescope, so it'll be something like Hubble as well. But these are all being studied right now as we speak. Plato will be launched in the late 2020s. It's like a TESS or a Kepler, but it has 26 different cameras, so it's going to be able to survey the whole sky too. Gaia is currently measuring where stars are, so we're finding new exoplanets based on how the star's orbit changes. And then there's really big telescopes. So this is a GMT, which is the Giant Magellan Telescope, which Arizona is actually building some of the mirrors for. So these are being built right now. These are things that are like 30 meters wide. That's really going to be able to look at new exoplanets in a way we haven't been able to do from the ground before. So to conclude, I hope I shared with you how looking at exoplanet atmospheres is a really exciting new field. We'll be able to look at things in the future that might indicate things like life, transits and eclipse, can help us identify exoplanet composition, temperature, and eventually habitability. Some directly imaged planets will also be able to do that with new technology. And the future is bright. We're going to keep making new missions to find new exoplanets and to characterize them in new ways. So I'll leave it with that.